All right. Good morning and happy Friday. We have a holiday weekend, and then next week is week 9, and then it's quick, right? Week 9, week 10, and then finals. So, just a few more things to cover. So on Wednesday, we introduced clustering. We introduced k-means clustering, which is a simple clustering algorithm, but it is effective. And in that clustering algorithm, we use Euclidean distance as our measure of similarity, and we assign points based on Euclidean distance, and whichever cluster centroid is the closest via Euclidean distance, we say, okay, that's the one it belongs to. There's some shortcomings of that method, and so we'll see a couple ways around that. And one is we can cluster via kernel functions, and that's what we'll look at today. And then next week, we will introduce the EM algorithm, which incorporates probability distributions onto our clustering methods. So we'll take a look at both of those kind of things. Okay. All right. So k-means clustering with kernel functions. Okay. So just a review of the k-means clustering algorithm. The way it works is we have to decide how many clusters that we search for. We consider the k here a hyperparameter. This is something that is not learned by the algorithm itself. It is something that we have to decide before we run the algorithm. Now, you can kind of automate the selection of k a little bit by perhaps having the computer loop through a bunch of choices of k, and then you use some metric to decide which of these seems to perform the best. But anyway, let's say you have your k determined. That would be, I guess, our step 0. Then we randomly assign points to each of your clusters, or you arbitrarily select some cluster centroids. And then once you have the points assigned to a cluster, you calculate the centroids, and then you reassign values, your different points, to the clusters by choosing the centroid that has the smallest Euclidean distance, and then you iterate back and forth. And so you reassign the points to the nearest centroid. Once you do that, you recalculate the centroids, and then if the centroids have moved, then you reassign points in case another centroid is closer, and then you recalculate your centroids, reassign points, go back and forth until you reach convergence, where everything kind of stays the same, nothing is changing anymore. And that's our k-means algorithm. And so just kind of an example here, I just have a bunch of points, and we start off with some random assignments. Some get assigned to black, some get assigned to red, some get assigned to green. These are just kind of the default colors R chooses if you say colors 1, 2, and 3. And so because of the randomness, these points, the centroid of black is right here, the centroid of red is up here, the centroid of green is there, and we're going to assign points to the nearest centroid. And so all of these points, they are closest to black, and then all of these points are closest to red, and it's only just a few of these points where the nearest centroid is green, okay? But that's okay. At least we have a few points assigned to green, so it doesn't just disappear. And then so we're going to say, okay, all the points currently assigned to black, calculate the centroid of them. All the points assigned to red, calculate the centroid. And so probably the centroid of red is going to be somewhere up here. And then for green, the centroid's probably going to be like somewhere around here, okay? Or I guess right there. And so this is what we get. And then now that we have new centroids, we recalculate, we reassign the points to the nearest centroid. And so all of these points over here that are currently assigned to red, they will get assigned to green because they're now a lot closer to the green centroid than they are to the red centroid. You know, some of these points will get reassigned, and this is what we get. All right, and then so now that we've done reassignment of points, now we're going to say, okay, what is the centroid of all of these points assigned to green, and what's the centroid of all of these points assigned to red, and what are the centroids of all the points assigned to black? And we recalculate, and they shift around a little bit. And now that we've moved the centroids, we're going to reassign the points, and so now these points over here, they are closer to green than red, and probably we'll draw some kind of line around here, okay? And so these got all reassigned to green and stuff, and then we're going to recalculate our centroids, and then we reassign points, we recalculate centroids, they shift around just a little bit, reassign points, and at this point, only a few points, if I switch back and forth, only a few points shift, and then recalculating the centroids it just moves a tiny bit. And I think at this point, nothing changes, which indicates that we've reached convergence, okay? So just kind of going through the animation, or just kind of like going through the slides, it looks like, you know, a little bit of a animation, and that's kind of where we've reached convergence. Okay. But again, the limitation or the shortcoming of k-means clustering in its kind of basic form is that its measure of similarity is Euclidean distance. And so I'm going to show you an example where Euclidean distance just doesn't quite work out. And so one thing we can do is we can apply you know, these transformation functions and calculate like kernelized distances. So we did this when we did SVM. So in SVM, we said we can apply this transformation function, which will take a point in, say, 2 dimensions and project it up into 3 dimensions, or, you know, 4 dimensions, or whatever. You have some kind of function phi that says, take this input, you know, your points are currently in 2D, you have some function phi, and it's going to transform it into something in a higher dimension. And so just a simple example is we can take our 2-dimensional vector x1, x2, and then we will transform it into 3D, and this will give us x1, x2, and then the third coordinate will be x1 squared plus x2 squared. And then so when you transform it into 3 dimensions, you can still get kind of a scalar value by doing the inner product or the dot product between xa and xb, okay? And this will be our kernel function. And so I can take xa and xb, I transform xa into, you know, 3D, xa1, xa2, xa1 squared, xa2 squared. And I do the same thing with b, xb1, xb2, xb1 squared, and xb2 squared. And then if I take the dot product or the inner product between these two things, we get this, xa1b1 and xa2 xb2, and this is equivalent to this, okay? Which means I could get this result directly without having to transform them into 3D first, okay? So yes, I can go from 2 dimensions to 3 dimensions and then take the dot product, or I could just take the 2-dimensional vectors and then apply this formula and then arrive at the same number. These are other possible kernel functions, okay? So if I have this kernel function where x1 and x2 become x1 squared, x2 squared, square root x1, x2, this, I can just take xa and xb and just do xa transpose xb and take that quantity squared. Or, you know, I could transform xa into 3D and xb into 3D and then take the dot product between them, and we would also arrive at the same thing. And there's other things. And one important one is this radial basis function kernel. And this one we just go straight to, we take our two-dimensional or whatever our vector in XA and XB, and then we can, do XA minus XB, transpose XA minus XB, and then take the exponent of that. To get the same answer, technically there is some kind of transformation function phi, but as far as the radial basis function goes, the transformation function phi takes your two-dimensional vector XA and it projects it into infinity dimensional space, which is kind of mind-blowing, but it's based on the Taylor expansion of the exponential function, which I don't know, you learn that's like in Calc 2 or somewhere along the way, right? You have the Taylor expansion of these functions, and that's technically an infinitely long series. And anyway, that there's a related transformation function, but we can't write it out and we can't calculate this coordinate because it has infinite components to it. But if we suppose we did try to do that, okay, and then we take the inner product, that inner product would result in whatever this thing is, okay? And so, all of our kernel functions are inner products of vectors after they've been transformed by that function phi, but we don't even need to think of the transformation itself. And so because this kernel function is basically phi applied to this, transpose phi applied to this, this is some inner product for some arbitrary transformation function, we can use a kernel function as a substitute for an inner product in the original space. So if you see XA transpose XB, this is an inner product in the kind of the original space. You can also just apply a transformation function. Okay. All right. So when we do k-means clustering, we assign a point to the cluster based on its distance to a centroid. And the squared distance of point x to the centroid, okay, so if you just wanted to kind of get like, this would be the x minus mu, this would give us like that distance vector, and then we can kind of square it, okay, and this would be the squared distance to that the centroid between point x and the centroid can be expressed as this, okay? And meanwhile, the centroid can be calculated as basically the mean of the points that belong to this thing, okay? So the reason why I show you this is because we want to get to a point where we can kind of calculate the distances to the centroid without actually calculating the centroid itself, which sounds kind of crazy, but we're going to get it into that form. And so we're going to say, well, this is how we can kind of measure the squared distance. This is our formula for the centroid. And so, this whole slide is just like crazy. Don't worry about it, okay? But basically, I'm going to replace, this mu sub k here as just a sum, basically the mean of the points assigned to that cluster, okay? So we're going to say, all right, what is the, distance from here to here? And so we're going to say, okay, we're going to calculate the mean of cluster K, and we can calculate the mean of cluster K here. And we can kind of expand all of this, and we get, and if you go through all of the math, you get through this kind of, I don't know, this mess here, okay? But one thing to note is that there's no mu's, okay? There's no actual centroid in here. Now, you say, well, that doesn't seem like we've made our life any easier, because mu is just, I take the points assigned to the cluster, I add them up and divide by how many I have. So that's pretty simple. why would we bother making my life much harder by having all of these kind of products between, XM and all of this stuff? And this just looks like a whole lot worse with all of this double summation stuff. Okay. The reason why is because eventually we're going to move to kernel functions, and or I guess just on the next slide we'll move into kernel functions, and this allows us to keep the distance. So this whole thing, as messy as it is basically the distance to the centroid. Okay, and this distance to the centroid is based off of all of the other kind of the x points that belong to that centroid. Okay, and what I have here is I have these inner products. Okay, inner products between xm, xr, and whatnot. And all I'm going to do is I'm going to just say, okay, well, wherever I see one of these inner products here, or these, x transpose x, I'm going to replace it with a kernel function, because a kernel function is also an inner product. Okay. This is cut off here. But basically, this indicator variable z allows us to calculate the sum of the similarities for only the points that belong to that cluster. So if we replace the inner products with the kernel functions, we now have a kernelized distance. Okay. So all we've done is we got into this form with all of these kind of x transpose x business, and we are going to just say, okay, well, wherever I see an x transpose x, I'm going to just have a k, all right? And this kernel function, remember, we can think of just as the inner product between a transformed x thing, okay? And so we're going to use this. And this allows us to calculate distances to the centroid without actually having to calculate the centroid itself. All right, this is a weird thing, okay? So it's a little bit of a weird thing. Okay, so I want to show how this kernelized k-means clustering works. And, okay, did I give you any quiz answers here? Okay, let me give you your first one. First one today is E. E as in elephant. All right, so, this is equivalent when we do kernelized k-means clustering. Okay, we could imagine taking our original data, applying this transformation function phi, kind of, and then once we have it transformed, then we perform k-means clustering on this transformed space, and then once we have the cluster assignments, we go back to our original data and we say, all right, these are the clusters that we formed. By using this formula here, we can just directly calculate the distances to the centroids without actually calculating the centroids itself. So this feels really weird, but we're going to assign values to new clusters based on the distances to the centroids, and then once we do that, we'll recalculate the distances to the centroids. So it used to be calculate your centroids, then calculate the distances and reassign based on the distances, okay? And then once you do that, recalculate your centroid, then calculate your distances and reassign based on the distances. Now it's going to be calculate the distances to the centroids, reassign points, then recalculate distances to the centroids and reassign points without actually calculating the centroid. And again, it feels totally kind of crazy, but it works. Maybe I'll jump to the very last slide here where I have kind of an explanation here for like how this works, just conceptually. But it's kind of, and so I wrote, the most amazing thing about this kernelized k-means thing is that the location of the centroid, which exists in this higher dimensional space, doesn't need to be calculated. The actual location of this centroid in this high dimensional space is left undefined, and instead that the distance to the centroids is expressed as an inner product that can be calculated, and we can think of these inner products as similarities between the different points. And basically, when you're calculating these distances to centroids, you're doing an inner product between basically every point and every other point. Okay, you're kind of measuring a similarity between this point and every single other point. And by comparing each point to every other point in the data, we can get a value for the distance to the centroid of each cluster. Okay, and so this kernel trick allows us to work with the result of the transformation, the inner products, without ever running the transformation function phi itself. And so we get the power of the higher dimension without the computational cost. I was kind of wrestling with like, how do I relate this to something that, so I have this analogy, and this is not a perfect analogy, but, imagine like trying to form friend groups, okay? Or like, in high school, I feel like every movie with high school students, there's like these kind of cliques and stuff, right? And then you have like the band kids, and you have the athletes, and you have the, I don't know, I'm thinking of like Mean Girls, and they have the plastics and stuff, right? And how does this thing form, okay? And so the problem is that no one tries to match themselves to a theoretical perfect friend or the central idea of a friend group. Like in movies, it's nice it's convenient to just say like, these are like the band kids, and therefore like they're like the centroid is like this imaginary average band student or something. But in reality, we don't necessarily have like this central idea of a friend group. Okay, the ideal of a group is some complex, impossible thing to define. It could be based on humor, shared history, political views, or some common interests or something like that. And so what actually happens instead is people kind of look at each other, and a person might kind of think like, I feel like I'm going to get along with this person, or we have a similar vibe or whatever, and there's like a measure of similarity that people have with one another. Okay, and so this is kind of the pairwise similarity. And then to figure out what group to join, a person doesn't compare themselves to the abstract ideal. Instead, they say, which of these groups as a whole do I feel most collectively similar with, like by looking at kind of the other individuals in that quote cluster, right? And so they're in effect averaging their similarity score with everyone else in that potential group and choosing the one that kind of fits best. And that's kind of how our kernelized k-means works. The people would be like our data points, and this reasons for friendship is like this high dimensional space that we can't like fully define, based on all of these, like how do you define what a person is and their personality, and it's like all of these different interests and whatever, okay, history and stuff. But we don't actually need to know that higher dimensional space. Instead, we have this measure of similarity that kind of exists in our local space or whatever. And again, not a perfect analogy, right? And it gives us a similarity score without figuring out the underlying reasons. And then, whatever you say the quote vibe of a friend group is, that could be thought of as like the centroid of that cluster, right? And it's not a person, it's some concept defined by the collective similarities of that group. And then the algorithm is then able to kind of calculate a point's distance to this quote vibe without ever, I don't know. Okay, so this is kind of like, because it just felt weird. Like, how do you calculate the distance to a centroid if you don't actually know where the centroid is, right? But then like, it's again, we kind of do something like that by saying like, okay, here's a group of people, and I feel like I'm going to get along with these group of people. Even if I can't really define what this group of people represents, I can say like, well, I get along with that individual and get along with that individual and get along with that individual. So probably I'm going to get along as a whole as this kind of collective, right? Versus this other group, even if I can't really define what this other group represents, I'm going to say, well, you know, I don't feel like I have much in common with this individual, or much in common with this individual, or much in common with this individual. So as a whole, I don't feel like I really belong in that group, right? And that's kind of how this kernelized thing is working, in that we have this we get a distance metric to these centroids without actually calculating the centroids itself. Okay, it is equivalent, however, to like if you were able to actually project it into that higher dimensional space. And so I do have kind of this, what I think is a neat little, where did it go? Of course, always RStudio. All right, let me. Install these packages. Okay. Where am I? I'm here. Okay, so we're gonna run all this stuff. All right, so here is so we have this very kind of simple data set. I've got 8 points, 4 in the middle here, and then 4 on the outside. Now, if we just use plain old k-means clustering, where we use Euclidean distance as a measure of similarity, okay, there is no solution of regular old k-means clustering where this point at -2, -2 ends up in the same cluster as 2, +2, because according to Euclidean distance, these two are as different as possible. Okay, like they are far apart, so they are very different according to Euclidean distance. But you know, I don't know. If I look at this, I feel like, okay, well, these in the middle should belong together, and maybe these ones on the outside we would put together, even if even if they are kind of different. Like they do, there's something that feels like we should put them into that thing. So, you know, a solution is we would project it into this higher dimensional space by using this transformation function. We would do x1, x2, and then x1 squared, x2 squared. And if we do that, we get 3-dimensional coordinates, our coordinates in 3D, okay? And it looks like this. And let me plot this. And we actually have this. Why didn't this work? How do I? I want the little thing to pop up here. Oh, here. This is what I want. No? Oh, okay. It did work. It did work. I just didn't see it. All right. So this is supposed to represent our points. Okay. So when we initially randomly assign points to, I initially assigned points at random to a cluster, and I had like 2 red points here, 2 blue points, and there are 3 points up here and a blue point there. And this, I don't know if you can you see this? This is red, 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 and then there's 1 blue point there, 2 red points and 2 blue points. And so this point represents the centroid of the 5 red points in 3-dimensional space. And so you can see because we have 3 red points and 2 red points down here, like vertically in the z direction, it's pulled closer to the 3 red points. And then from top down, I've got a point here, here, and here, and nothing in this corner, and so the red one gets pulled in this direction. Whereas for blue, I've got 2 points in blue here and 1 over here, and so the center of blue in that direction is over there. And then I've got 1 up high and 2 down below, and so the average of is I don't know. Okay, so anyway, these are the centroids of our current cluster assignments in 3 dimensions. And then so based on this, we say, okay, let's recalculate the distances to each centroid, and then we will assign each of our points to the nearest centroid. Okay, so if I do that, then basically, so this is that plot in 3D. And then we reassign the points, and basically all of the points in the upper layer and the top get assigned to one cluster, and then all the points at on the bottom in the center get assigned to the other cluster. And so this is what it ends up looking like there. So after doing that, okay. So this is the end result. So these ones up here all get assigned to red, and then the 4 points down there all get assigned to blue, and so this is the resulting cluster assignments at the end, right? And I think it's kind of hard to tell, but this is what the plot is supposed to. Something like this, right? Okay. This point is this point that's floating up here. Okay, so that's what we end up getting, and that's how k-means clustering works after we've applied the kernel function to again project it up into 3 dimensions. Okay, now we can do that. We can go from 2D to 3D, calculate the distances, and reassign the points. Okay, but we can also just do it directly without actually calculating the centroids. Okay, so in this slide I said, okay, well, this is, once we project it into 3D, this is the centroid in 3 dimensions of cluster, the red cluster and the blue cluster. These are the actual centroids, and we can calculate the distances by doing, this minus this squared plus this minus this squared plus this minus this squared. We can get the distances to those centroids. But we can also get these same distances. So just remember this number, 23.265 and 7.984. We can get that distance directly using this kernelized function, okay? Using this kind of this inner product business and double summation, and I have all of this, and if I do it, I get this big mess, and I calculate all of this, but I get the distance from the first point to the centroid of cluster A as 7.984, okay? And these are all of the other distances in that column, 7.984, 8.251, 7.718, and it's the same as these ones right here, 7.984, 8.251, 7.718, so on and so forth, okay? And we can get all of the distances there. And similarly, we can get all of the distances to centroid B as using this same formula, okay? As messy as this thing is, it allows us to calculate the distances in that higher dimensional space without actually having to calculate the centroids in that higher dimensional space, okay? And then, and so by doing that, we can then reassign our cluster, redo our cluster assignments, and get our clusters. And so we have cluster 1, cluster 2, and we end up with the same results. Okay, let me give you your second view quiz answer, which is the letter C. C as in cat. Yeah, question. Is the quiz closed? Oh, okay. What have I done? Week 8, Friday. Available. Oh, yeah, that's not going to work. All right, today is 23rd. Okay. All right, that should now be available. Okay, so E and C. And then, okay, so all to show that it kind of works here. And so we can calculate the distances A and the distances to B, and it's this kind of big mess, but it works. And we reassign, and we get the results. Okay, so here's again just another artificial example, and I'm going to start off with kind of these two circles of points. I have this ring of points on the outside, and I have a ball of points on the inside. Okay, I guess all of this is in two-dimensional space. And if you just try to do regular old k-means clustering, this is the result that R does. Again, it's using Euclidean distance and says, okay, well, I'm going to just put these ones together, but then all of these points, they belong together because, again, with Euclidean distance, the points up here and the points back here, down here, are far apart, and so Euclidean distance says they are very different. Okay, and well, we can say, well, you know what? Let's try applying a kernel function, and so the kernel function I'm going to apply is I'll use the Gaussian or the radial basis function, and again, that projects it to a higher dimensional, this infinity dimensional space, and so it's going to be impossible for us to calculate the actual centroid location. Okay, how do you define what that centroid location is? We're not going to be able to do it, but we're able to get distances to that unknown centroid, again using kind of this measure of like we're going to measure the similarity from this point to every other point, and by kind of seeing how similar this point is to every other point in the data set in our kind of current dimensional space, we can get the distance to the centroid in that higher dimensional space. And so, here I'm going to do random assignments to our clusters. So we just have a mix of this, and then we'll iterate back and forth and reassign. We just reassign our points to the nearest centroid, okay, even though we don't actually know where that centroid is. And so this is just the code to do that. This is how we're going to calculate our distances to centroid A and our distances to centroid B without actually figuring out the centroid location of A and centroid location of B. And we're going to just kind of reassign our points, okay? So this is after one iteration, it reassigned points, some to red and some to black. And again, we have no idea. I have no idea what is actually going on in the higher dimensional space, but this is kind of our group assignments there. And then after our second iteration, now all of the points on the outside are all in cluster, the red cluster, and then these ones, we're kind of split. And then if we go again, we get a few more, and then here we get this, and then at the next iteration, no changes, and we'll say it's converged. Okay, so we just kind of run the thing over and over and over again, reassigning points to the nearest centroid. And that's that. Okay, and I think these are the slides that I already covered about like how this works. And again, it feels very strange being able to calculate your distance even if you don't know the actual location of the other centroid. But it's because we do have every other point in our data, and we know based on our current assignments, we can say all of these points belong to this cluster and all of these points belong to this cluster. And because I'm able to kind of compare this point to every other point in that cluster, we can say, all right, this is how similar we are to that cluster. Okay, that's it for today's lecture regarding kernelized k-means clustering. Okay, so it's still this iterative process of reassigning points to different clusters, but now there's no recalculation of the centroids. Okay. All right. Last answer today is the letter B. B as in bear, and we'll call it a day. Have a great weekend. Enjoy the holiday, and we'll see you on Wednesday.